this segment, we're going to talk about the entropy balance for an open system. So remember, entropy, unlike energy and mass, it's not conserved. Here we've got an entropy balance because we can't do an entropy balance. And you'll also notice that I've got things in terms of rates for an open system because typically we have things in terms of rates. We've got mass flow rates, we've got heat transfer rates, power rates, or work rates, which is just power. So it's the rate of change in entropy contained within the system equals the net rate of entropy transferred into the system plus the rate of entropy produced within the system. So the first part of that is the rate of change of entropy contained within the system, and that would be ds dt. And if it's a steady flow process, then that term just goes to zero. Then you've got the rate of entropy transferred into the system. And for an open system, you can transfer transfer entropy two ways, and that's by heat transfer and by mass flow. And we're going to come back to that heat transfer in just a minute. Plus the rate of entropy produced within the system. So it's a rate. So we'll put a little dot on the top of that, sigma, just to indicate that it's a rate. And the units on all of this are going to be kilojoules per second Kelvin. If the problem asks for the rate of entropy produced per unit mass, per kilogram of whatever flowing through this control volume, then it's asking for sigma dot divided by m dot. And so the units you can see will give you kilojoules per kilogram. So just be aware of that little verbiage. I'll try, on a test, I'll give you the units in addition to that verbiage. So if I'm asking you for the rate of entropy produced per unit mass, I'll say, in units of kilojoules per kilogram K or BTU per pound mass degree Rankine, so it's clear. So going back to that heat transfer term, if that process is adiabatic, then that's pretty easy. That term is just zero. Now, typically what you do is instead of, the temperature, that it's the temperature in the denominator there, that's the temperature at the system boundary. And in reality, the temperature at the system boundary is typically not going to be a constant. So for example, if you've got a turbine, you've got your working fluid coming in, and it's coming in at a high temperature and high pressure, and then by the time it expands and it comes out at the outlet, it's cooled down. So the temperature of the boundary at the inlet of that turbine is going to be a lot higher than the temperature at the outlet. But what we do in this class is we just take the average temperature over the entire boundary. And if that's the case, then that summation becomes really simple, and it's just Q dot divided by T, where T is the average boundary temperature. And the problem will tell you what the average boundary temperature is. You won't have to calculate that for yourself. All right, well, I hope that was helpful, and thank you for watching.